through of that test review. Let me know if I make mistakes because I'm going to do this in real time, and then things can happen when you're talking and doing calculations at the same time. I misread or do something funny. Addition is usually my downfall. First one says to find the derivative of this, so I'm going to do f prime of x, and we're just doing the power rule, so that'd be 10x to the fourth. Just email me if you have trouble with the power rule and don't know how that works. Number 2 down here, that f prime of x, it's just a series of those power rules. When you have a polynomial, you just work down the line. So you get negative 18x to the fifth, and this would be minus 16x to the third. So I went through the first two. And finally, the derivative of negative 4x is just negative 4. Done. And the derivative of the constant, remember, at the end, that's 0. And that's our derivative right there. No need to do any work with it. It just is. The next two, the slope of the tangent line to the graph for specific points, like where x is. And you'll notice that when I take the derivative, I'm only putting in the x value. There's no place to plug in the y. And that really just says all I need is x to tell me where I'm trying to find the slope of the tangent line. So this first curve, 4x to the fifth, we'll call it part A. I'm just going to squeeze it down here underneath. You want to get the derivative, but that's only step 1. So I go 20x to the fourth plus 9x squared minus 2x. Starting to like those derivatives, aren't you? And then what I need, though, the slope of the tangent line at this curve at 0, f prime of 0. If I put 0 in each one of these, you're taking 0 to the fourth, you're putting 0 to the second, and I think you all know what's coming. Just multiplying by 0 in general is 0. So we're just getting out 0 in each of these cases. So that means for this particular curve, I happen to know what it looks like. It's one of these, whatever you do is you look at that at 0, that tangent line, if I were to draw it in there, would have a slope of 0. It would go flat at that particular location. So that's what a derivative is for. Ideally is to find out the slope of tangent lines at various points. And tangent lines means just how it would rest on there. A tangent line can pass through, but it just can happen anywhere along the curve. You just rest a rigid rod against the curve, and how it slopes is the slope of the tangent line. The only one that kind of catches us is like at places like I'm highlighting right now at 0 right in there. That slope is 0. The tangent line will pass through, but the slope at that particular moment, the rate of change, is in fact 0. Okay, so we're going to go to part B on this one. Derivative in part B, y prime would be 10x minus 2. And for that one, it says, hey, what's the at x equals 1? So what I'm going to do is put 1 in to this function. And so it'd be 10 times 1 and minus 2. So I'm going to get 10 minus 2, which is 8. The slope of the tangent line is 8 at that spot. Okay, so there's A and B, put a line between them. 4, find the derivative of this function. H prime of t is, you just do the same power rule. Those negatives shouldn't bother you. Negative 3t, and then subtracting 1 from negative 3 makes it negative 4. And then the negative 1 that you see in here times the negative 8 out front makes it a positive 8t, and then subtracting 1 from negative 1 makes it negative 2. So there's your derivative. Nothing fancy. Just wanted to see a derivative with some negatives in there. Number 5 has some algebra before you differentiate. That's another word. It's a verb for take the derivative of. But I would rewrite this. I'd do a little work. There's a couple things I'd do. One, I'd distribute the power, because when you do a power or an exponent of a product, you can distribute it. So this is not the derivative, though I really think sometimes when you're doing all this, we all get distracted and think, hey, maybe I'm done. Maybe I did all my work. But be careful, this is just algebra. Distributed the power, 2 squared is 4x squared. One of the things that we've talked about in class is that you can take that x squared and move it up top, and that's what you want. So I got 3x to the negative second over 4. That negative exponent allows us, that's the rewriting of x squared in a different place in the fraction. And then you can pull them apart and call this just 3/4 x to the negative 2. That's rewriting. That's equivalent to what we started with back here in the beginning, but now we're dealing with it in a way that's much easier to take the derivative of. And so the hard work is the algebra, as in calculus it often is. So in this case, y prime would be the derivative of this version here, and I'm going to call this, we're going to take negative 2 times 3/4. So I'm just going to do it all, just kind of show you. Negative 2 times 3/4, and then x to the negative 3, because you're taking away 1 from the power. And when you multiply a number and a fraction, you multiply the number times the numerator. So this becomes negative 6/4 x to the negative third. This is perfectly good. Can go with this, but for pie in the sky later on when we want to simplify a little bit more, what we do is 6/4 simplifies to 3/2, so it'd be negative 3/2. And what I do with that negative x to the negative third often is I'd put it down in the denominator as x to the positive third. This would be like the super duper answer that goes with it. However, we've actually been good to go since, let me get a different color here, put in some blue. These circled answers all are okay. It's just there's a level of ideal depending on your circumstance. This one's just the extra cool one on the end where it's all simplified. To number 6 down below, this one's, it is an interpretation. It's just taking some data like anyone would in a situation where you're trying to run a business. You need data on your population arriving through the door. So here is t equals 1 is January, so just interpreting what the graph is, and visitors to a national park in hundreds of thousands, so that's all good because we're going to need units when we're done. It says estimate the rate of change of v over the 5 to 8 interval, and I think that it got chopped off. So let me write that in the interval, which should be written in there, 5 to 8. So we're going to go from 5 to 8, which if I mark points on this graph, 5 and 8, what I'm going to do is the rate of change is going to be a slope of a secant line, especially when we're estimating. It's the average rate of change. So you want to always draw a secant and find its slope. That's what we're going to do. So draw secant, find its slope, and here goes. What I do is rise and run. So let's do some rise in green. So if I go in here and do the rise, I think we're going from 900 to just under 1500. So I don't know, here's 1250 in between there. What if we said 1300? Wouldn't that be fair? So I'm going to call this like 1300 tall. And this is estimating, so you don't have to get all bogged down in the dirty details of it, but I think we're okay to go to 1300-ish, 1340, maybe even 1400 if you want to, maybe 1350. But I was just thinking of him halfway between would have been 1250, something like that. So 900, 1000, 1100, so 1200, 13. Oh, wait, is that right? So I get about 250. It was halfway. I'm misinterpreting that, right? So this is where you guys can email me funny questions. It's a difference of 250 between them, so this would be 1450 in between those, a difference of 250. So I don't know. So we're going to call that like, could you call it 1450? Something like that. Yeah, it's a tough call. I'm going to go 1400 and just maybe give that a ballpark fix. I am giving you some leeway, and I think you guys have noticed when we did this on my math, WebAssign, it's something like that too. It gets close in between. It's pretty accepting. So I'll throw 1400 in there. This one's 900. And then left to right, we're doing from 5 to 8. So what we're dealing with on there is 3 months worth. So from here to here, this is our run. Looks like a passage of 3 months. Okay. The reason that's important is because that's what we measure. We're doing rise over run. So for us, it's going to be a slope, an approximate slope of, I'm thinking, maybe 500 rise, and then a run of 3 months, and this is 500, 100 millions of dollars, 100 thousands. So I'm thinking 100 thousands of dollars, big bucks, and then this is 3 months. Now the reason that's important is that if you simplify 500 divided by 3, use your favorite method, that in itself is enough to give me the average rate of change on there. If you want to go get the decimal, that's fine. But if you do the decimal, what you're going to do is combine these units. The units is always change in y per 1 unit change in x. So just a quick calculation away. Sorry, just somebody walked in my door here, but I'll get that taken care of. 500 divided by 3, get back to where I was. I get the total of 666 2/3, or 6.6, we call it 6.7, so this would be 160, so it would be 166.67 hundreds of $1,000s per month. Hundreds of thousands. Is it dollars? Oh, people. Of people, not dollars. Thinking a different problem. Of people, PPL, per month. And that's when you do a rate of change, if you simplify it down to some decimal like this, you want to make sure it's change in y per 1 unit change in x. Okay? Down to the bottom, number 7. We'll do this as part 1 of the video because they get long. I'll just say it's a video for help on 1 through 7, and then I'll load up a PDF of this too for you guys to use. Marginal cost means the derivative of cost, so it's really C prime. Nothing fancy about that. It's 9,800. What that tells us, if you were to graph this, that's linear. Your costs are just going up like this. It's a line, and so when I ask you what for the slope of the tangent line anywhere on that curve, which is what a derivative does, you're going to find that this always has a slope in 9,800. And we knew that from reading the equation too. Remember, the slope is with the input variable x in this case. And it turns out the slope of the tangent line will always be 9,800 because anywhere we rest a tangent rigid rod against this curve, it will always have that same rise over run. Okay. All right, that's part 1 of this video. I'll get you part 2 here pretty shortly.